30 AWS Java Debugging Scenarios.
Welcome back. For Java developers working in AWS, distinguishing between application errors and infrastructure constraints is a critical skill. When a microservice fails in production, standard exception logs often fail to tell the whole story. You need a structured approach to root cause analysis.
Real-world diagnostics.
In this video, we are moving beyond basic syntax errors. We will examine 30 complex, real-world debugging scenarios that define senior and principal engineering roles. We will cover memory leaks, network latency, database locking, and distributed tracing inconsistencies.
The methodology.
For each scenario, we will follow a strict diagnostic framework: the symptom, what the alert says; the common assumption, what usually leads to a dead end; the root cause, the actual technical issue; and the resolution, the specific code or configuration fix. Chapter 1. Memory and Resource Management.
Scenario 1. The Fargate OOM crash.
You have a standard Java Spring Boot application running on a WSECS Fargate. The service appears healthy, but every 48 hours, the container terminates unexpectedly. The logs do not show a stack trace or a Java out-of-memory error. The only evidence is an orchestration event reporting exit code 137.
Common assumptions.
The immediate assumption is usually that the Java heap is exhausted. Developers often respond by increasing the XMX, max heap size, settings in the Docker file, assuming the application requires more memory. However, this often accelerates the crash rather than preventing it.
The root cause. Native memory overhead.
The issue is rarely the heap itself. It is the native memory usage exceeding the container's hard limit. Exit code 137 indicates the Linux OOM killer terminated the process. By allocating too much memory to the heap, we leave insufficient room for non-heap components. 1. Metaspace class metadata loading. 2. Thread stacks memory allocated per thread. 3. Direct byte buffers, used heavily by AWS SDKs and NATI for I or Os. 4. Garbage collector operational overhead. The resolution, NMT diagnosis and RAM percentage. Disclaimer: always test code in a non-production environment. First, we enable native memory tracking, NMT. This JVM flag allows us to inspect off-heap memory usage, helping us confirm if the leak is occurring in metaspace or direct buffers. Second, we remove the static XMX flag. Instead, we use max RAM percentage. This instructs the JVM to calculate the heap size based on 75% of the container's total available memory, automatically reserving a 25% safety buffer for native overhead.
Follow-up 1. Since we cannot easily access a shell in a production Fargate container to run JCMD, how do we monitor native memory usage?
Answer: we cannot rely on standard CloudWatch metrics as they only show total container memory. The standard solution is to attach a sidecar agent or use the Prometheus JMX exporter. We specifically configure it to export java.neo.bufferpool metrics, which exposes direct byte buffer usage to our observability platform.
Follow-up 2. Native memory tracking metrics appear stable, yet the operating system's resident set size, RSS, continues to grow until the crash. What is the discrepancy?
Answer: this indicates memory fragmentation within the Linux memory allocator, GLIPC. The JVM may be releasing memory, but the OS allocator is not reclaiming it. The resolution involves setting the environment variable malloc_arena_max equals 2, which restricts the number of memory arenas and forces better memory consolidation.
Follow-up 3. Curveball. The Java metrics are healthy, low heap, low native memory, yet the ECS task still terminates with exit 137. What is the likely external cause?
Answer: the issue is likely a noisy neighbor sidecar container. In ECS, memory limits are often defined at the task level, shared by all containers. If a logging agent like FireLens or monitoring sidecar lacks strict resource limits, it can consume the shared memory pool, causing the kernel to kill the largest process, which is usually the Java application.
Scenario 2. The Sawtooth CPU spike.
Your application performance monitoring dashboard reveals a distinctive sawtooth pattern in CPU usage. The CPU usage gradually climbs over several minutes, drops sharply, and then immediately repeats the cycle. Coinciding with the CPU drops, you observe latency spikes where requests momentarily hang or timeout.
Common assumptions.
Engineering teams often misinterpret this as a load balancing issue or an infinite loop within a scheduled task. They typically respond by vertically scaling the instance type to add more CPU cores, which paradoxically can make the pauses longer rather than shorter.
The root cause, stop the world garbage collection.
This pattern indicates the Java virtual machine is struggling with memory reclamation. The gradual rise is memory filling up. The sharp drop is a full GC event where the JVM pauses all application threads to clean the heap. 1. Allocation rate. The app creates objects faster than the young generation can clear them. 2. Promotion failure. Short-lived objects are being promoted to the old generation unnecessarily. 3. GC pause. The throughput-optimized parallel GC, default in older Java versions, freezes the app to compact memory. The resolution, switch to concurrent collectors. Disclaimer, always test code in a non-production environment. Before applying fixes, we must validate the hypothesis. We enable unified JVM logging to capture exact pause times and generation sizes. This log file is the black box recorder for JVM memory events. We replace the default collector with ZGC, generational mode. Unlike legacy collectors that stop the application to compact memory, ZGC performs expensive memory operations concurrently while the application runs, keeping pauses under 1 millisecond regardless of heap size.
Follow-up 1. If we cannot change the Java version to use ZGC immediately, how do we tune the existing G1 GC collector to reduce these pauses?
Answer, we manipulate the max GC pause millis flag. By default, G1 GC tries to balance throughput and latency. Setting Roman 20, max GC pause millis equals 200 forces the collector to adjust its heuristics, like young gen size, to meet that latency target, prioritizing responsiveness over raw throughput.
Follow-up 2. The GC logs show massive premature promotion. Objects are moving to the old generation before they expire. How do we fix this without changing code?
Answer, we need to increase the tenuring threshold. By increasing the young generation size, Roman 20, new ratio, or specifically setting survivor ratio, we give objects more time to die young. This prevents short-lived transactional objects from polluting the old generation, which is expensive to clean.
Follow-up 3. Curveball. You enabled a concurrent collector like G1 or ZGC, but now the application throughput has dropped by 15% and average CPU usage is higher. Why?
Answer, this is the concurrent overhead tax. Low-latency collectors use background threads to clean memory while the app runs. If your container only has 1 or 2 vCPUs, the GC threads are fighting with your application threads for processor time. In resource-constrained environments, the stop-the-world serial GC might actually be more efficient.
Scenario 3. The ghost threads.
The application performs normally after deployment, but over the course of a week, the EC2 instance becomes increasingly unresponsive. CloudWatch metrics show memory is stable, but the thread count metric climbs linearly. Eventually, the application stops accepting new connections, even though traffic volume has not changed.
Common assumptions.
The standard assumption is a network deadlock or a database query hanging indefinitely. Teams often restart the server to clear the pipes without identifying the source, treating it as a transient network glitch.
The root cause. Thread leaks via unbounded executors.
The application is creating threads that are never terminated. This usually happens when 1. An executor service is created inside a method but never shut down. 2. Asynchronous clients like a AWS SDK are instantiated on every request. 3. Threads are waiting on a resource that never responds, missing timeouts. The resolution, named thread pools and lifecycle management. Disclaimer, always test code in a non-production environment. First, we stop using default thread factories. We explicitly name the threads, for example, payment worker. When we take a thread dump later, we will see 1,000 threads named payment worker instead of pool 1 thread 5, instantly identifying the leaking component. Second, if an executor service is created within a request scope, which is bad practice but common, it must be shut down in a finally block. Without this, the pool remains active in memory, holding its threads alive forever, eventually hitting the OS thread limit.
Follow-up 1. We identified the thread leak, but we cannot redeploy immediately. How do we confirm the exact line of code causing the blockage on the live server?
Answer: we trigger a thread dump using JStack LPID. We look for threads in the waiting or timed _waiting state. We analyze the stack trace of those specific threads to see exactly which method call, for example, HTTP client.send, they are stuck on.
Follow-up 2. You see performance degradation across the entire app, but no specific thread leak. You notice widespread usage of parallel stream parentheses in the code. What is the danger here?
Answer: all parallel stream parentheses operations share the single JVM-wide fork join pool.common pool parentheses. If one task performs a blocking I or O operation, like an S3 upload, inside a parallel stream, it blocks a worker thread for the entire application. This can starve all other parallel streams in the system, causing a cascading slowdown.
Follow-up 3. Curveball. The thread dump shows threads stuck in socket input stream.socket read 0, but you have definitely set a connection timeout in your HTTP client. Why are they still stuck?
Answer: connection timeouts only apply to the initial handshake. You are missing the read timeout, so _timeout. If the server accepts the connection but simply stops sending data bytes, a black hole server, the client will wait forever unless a specific read timeout is configured.
Scenario 4. The metaspace bomb.
You are running a legacy Spring application on Tomcat within an EC2 instance. The application runs smoothly for days. However, after the third hot deployment, deploying a WAR file without restarting the JVM, the server crashes with a java.lang. out of memory error metaspace. The heap usage is normal.
Common assumptions.
The standard reaction is to simply increase the Roman 20 max metaspace size setting. While this buys time, it does not solve the problem. The crash will eventually happen again, just after the 5th deployment instead of the 3rd.
The root cause, class loader leaks.
Metaspace stores class metadata. When you redeploy an application, the old class loader and all its loaded classes should be garbage collected. If they are not, it is a class loader leak. This happens because 1. A thread local variable was set but never removed. 2. A JDBC driver registered itself but did not deregister. 3. A background thread started by the app is still running, holding a reference to the old class loader. The resolution: cleaning up thread locals. Disclaimer: always test code in a non-production environment. Thread locals are the #1 cause of metaspace leaks. If a thread, from the server's thread pool, survives the application redeploy, this variable keeps pointing to the old class definition, preventing the entire class loader from being garbage collected. We must implement a servlet context listener. In the context destroyed method, which runs on shutdown, we strictly clean up resources. Calling remove parentheses breaks the reference chain, allowing the JVM to reclaim the metaspace memory.
Follow-up 1. We suspected a leak, but how do we prove which specific class is holding the reference to the old class loader?
Answer: we capture a heap dump using JMap. Then, we use a tool like Eclipse MAT Memory Analyzer tool. We look for duplicate classes, the same class loaded by different class loaders, and run a path to GC roots query to see exactly which static variable is keeping the old class loader alive.
Follow-up 2. We fixed the leaks, but metaspace still fills up, even without redeployments. The application uses a lot of AOP and XML serialization. What is happening?
Answer: this is dynamic class generation. Frameworks like Spring AOP, Hibernate, or JAX generate proxy classes at runtime, for example, MyService $enhancer by Spring cglib. If these are generated inefficiently or not cached, the JVM creates thousands of new class definitions, eventually exhausting metaspace. The fix is to cache the JAX contexts or review the AOP scope.
Follow-up 3. Curveball. Why does this metaspace OOM almost never happen in modern Docker or Kubernetes environments?
Answer: because modern architectures favor immutable infrastructure. We do not redeploy WAR files into a running Tomcat instance anymore. We tear down the old container and spin up a brand new one with the new code. The JVM process is fresh every time, Rendering class loader leaks largely obsolete in cloud-native deployments.
Scenario 5, the Docker memory lie.
You deploy a Java application to a Kubernetes pod limited to 2 gigabytes of RAM. The application starts, runs for a few minutes, and is immediately killed by Kubernetes OOM killed. However, your application logs show that the heap was only using 500 megabytes at the time of the crash.
Common assumptions.
Developers often assume the container limit is simply too tight and double it to 4 gigabytes. While this stops the crash, it wastes resources and masks the underlying configuration error.
The root cause, lack of container awareness.
The JVM, especially versions before Java 8 U191 or Java 10, queries the OS for available memory. In a container, the OS reports the host machine's memory, for example, 64 gigabytes, not the container's limit 2 gigabytes. 1. The JVM sees 64 gigabytes of RAM. 2. It defaults the max heap to 1/4 of physical memory, 16 gigabytes. 3. It attempts to allocate a 16 gigabytes heap inside a 2 gigabytes container. 4. The kernel kills the process immediately. The resolution, container support flags. Disclaimer: always test code in a non-production environment. Before guessing, run this command inside the running container or during startup. If it reports a max heap size that is larger than your Kubernetes limit, you have confirmed the container awareness issue. The flag Roman 20 plus use container support enables the JVM to read the cgroup's memory limits instead of the hardware specs. Combined with max RAM percentage, the JVM dynamically sizes itself to fit safely within whatever limit Kubernetes assigns.
Follow-up 1. Does this container lie apply to CPU as well? What happens if I set a CPU limit of 1 core on a 64-core host?
Answer: yes, it absolutely does. By default, runtime.get_runtime_available processors will return 64. The JVM will size its fork join pool and garbage collector threads based on 64 cores. This causes massive thread contention on the single core you actually have, degrading performance. You must verify Roman 20 active processor count matches your limit.
Follow-up 2. What happens if swap is enabled on the Kubernetes node and we do not disable it for the container?
Answer: this is a performance death spiral. Instead of getting OOM killed, the JVM will start swapping pages to disk. Garbage collection, which requires scanning memory, becomes excruciatingly slow because it is reading from disk instead of RAM. The app will not crash, but latency will spike to seconds or minutes. Always disable swap for Java containers.
Follow-up 3. Curveball. You set max RAM percentage to 75%, but the pod is still getting OOM killed during startup. What obscure setting is missing?
Answer: initial RAM percentage, or min RAM percentage. If the JVM eagerly commits a large initial heap before the application fully initializes, and there is a spike in native memory usage during startup, like class loading, the combined total might briefly exceed the limit. Tuning the initial heap allocation can smooth out the startup memory curve.
Chapter 1 Summary.
We have covered the invisible threats, native memory fragmentation, stop-the-world GC pauses, thread leaks, class loader retention, and container unawareness. These are the issues that kill applications silently. Now we move from the internal memory of the JVM to the external chaos of the network. In Chapter 2, we tackle the problems that work perfectly on your local machine but fail mysteriously in the cloud. Next up, the it works locally, but not in AWS scenarios.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts. saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Chapter 2, the It Works Locally Trap.
We have secured the JVM's internal memory. Now we face a more chaotic environment, the network. Localhost is a deceptive environment with zero latency, infinite bandwidth, and no firewalls. In AWS, the network is unreliable, latency is variable, and connections fail.
Distributed systems nuances.
This chapter covers the issues that vanish when you debug locally but paralyze production systems. We will diagnose connection pool exhaustion, black hole timeouts, DNS caching persistence, and cold start latency.
Scenario 6, the connection pool freeze.
Your Spring Boot microservice connects to an AWS RDS Aurora database. Suddenly, the application becomes unresponsive. All worker threads are in a waiting state. However, when you check the RDS monitoring console, the database CPU is near 0%, and there are plenty of available database connections.
Common assumptions.
The natural instinct is to blame the database performance or network latency. Developers often restart the database or scale up the RDS instance, but the application threads remain stuck immediately after the restart.
The root cause, connection pool exhaustion.
The bottleneck is not the database. It is the client-side connection pool, likely Hikari CP. The application threads are blocked waiting to borrow a connection from the pool, but none are available. This happens because 1. Connection leak, code opens a connection but fails to close it in a finally block. 2. Long transactions, a query takes longer than expected, holding the connection and starving other threads. 3. Pool sizing. The pool is too small for the concurrent request volume. The resolution, leak detection and try with resources. Disclaimer, always test code in a non-production environment. By default, Hikari CP does not report leaks. We must set a leak detection threshold, for example, 2,000 milliseconds. If a connection is held longer than this, Hikari will log a stack trace pointing exactly to the method that borrowed it, exposing the leak. The programmatic fix is to enforce the try with resources pattern. This creates a safety net where the JVM automatically calls. Close parentheses on the connection when the block exits, guaranteeing the connection returns to the pool.
Follow-up 1. Leak detection helps during debugging. But how do we monitor for pool exhaustion in production before it crashes the app?
Answer, we must monitor the Hikari CP JMX metrics, specifically threads awaiting connection and active connections. If active connection stays at the max pool size and threads awaiting connection starts climbing, you are about to freeze. Alert on this queue depth.
Follow-up 2. You increase the pool size, but now the application completely deadlocks. The DB is idle. What happened?
Answer, this is likely a pool locking deadlock. If a single thread requires 2 database connections simultaneously, for example, inside a nested transaction or a recursive call, and the pool size is smaller than the number of threads, the threads can consume all available connections while waiting for a second one that will never become available.
Follow-up 3. Curveball. The connection pool is healthy, but during an Aurora failover, the application hangs for 15 minutes before reconnecting. Why so long?
Answer, this is due to the max lifetime setting. If Hikari's max lifetime is longer than the network state, or DNSTTL, it holds onto dead connections to the old writer instance. We must set spring.datasource.hikari.maxLifetime to be slightly shorter than the database's connection timeout to force regular refreshment.
Scenario 7. The black hole API call.
Your application calls a third-party payment gateway or a partner a PI. Most requests finish in 200 milliseconds. However, randomly, a request will hang for exactly 60 seconds and then throw a generic I or O exception. The external provider claims their logs show no request received during that time.
Common assumptions.
Developers usually blame the external provider for downtime. They assume that if the request failed, the server must have sent an error. However, the exact 60-second duration is the telltale sign of a client-side configuration issue.
The root cause, default timeouts.
The request is hitting a black hole. This happens when a packet is dropped by a firewall or NAT gateway and no ACK or RSD is received. The client waits indefinitely or until the OS default kicks in. Java's default timeouts are often infinite or extremely long. 1. Connect timeout, time to establish the TCP handshake. 2. Read timeout, socket timeout, time waiting for data packets after connection. 3. The 60 seconds delay is often the default OS TCP retransmission timeout limit. The resolution, aggressive explicit timeouts. Disclaimer, always test code in a non-production environment. The connect timeout controls the TCP handshake. If we cannot reach the server in 3 seconds, we fail immediately. There is no point waiting 60 seconds just to find out the IP is unreachable. The read timeout is crucial for the black hole scenario. If the connection is established, but the server stops sending bytes, hangs. This timer kills the request after 5 seconds, freeing up the thread.
Follow-up 1. What is the functional difference between a connect timeout and a read timeout in a packet trace?
Answer: a connect timeout occurs during the SYN/SYNACK phase of the TCP handshake. No data has been sent yet. A read timeout occurs after the handshake, during the data transfer phase, push or ACK. It means the socket is open, but the input stream is silent.
Follow-up 2. We set timeouts, but now we see connection reset errors on sporadic requests. We are using a load balancer. What is the cause?
Answer: this is a stale connection issue. The HTTP client acts as a pool and keeps connections alive, If the load balancer has an idle timeout of 60 seconds, but the Java client keeps the connection for 120 seconds, the client might try to reuse a connection that the load balancer has already silently dropped. The fix is to set the client's connection time to live to be less than the LB's idle timeout.
Follow-up 3. Curveball. You are calling an external API from a Lambda function in a private VPC. The timeouts happen only during high traffic bursts. The external API status is green. What is the AWS bottleneck?
Answer: the NAT gateway. If your Lambda scales up to thousands of concurrent executions, you might exhaust the NAT gateway's port allocation, SNAT ports. Packets are dropped before they even leave your VPC, resulting in connection timeouts despite the external service being healthy.
Scenario 8. The DNS cache trap.
You perform a maintenance failover on your AWS RDS database, switching the writer node to a standby instance. The AWS console shows the DB is up and the DNS endpoint has updated. However, your Java application begins throwing connection refused or timeouts. It persists for minutes or even hours, continuing to try to connect to the old, dead IP address.
Common assumptions.
Developers often blame AWS Route 53 propagation delay or local network caching. They assume that restarting the application solves it because it forces a refresh, but they fail to fix the underlying configuration that caused the stale lookup.
The root cause, JVM DNS caching.
The Java virtual machine has its own internal DNS cache, separate from the OS. By default, under certain security manager configurations or older Java versions, the TTL time to live for a successful name lookup is set to forever -1. 1. The JVM resolves db.example.com to IP 1.2.3.4 once. 2. It caches this result indefinitely. 3. When RDS fails over to IP 5.6.7.8, the JVM never asks DNS again. 4. The app sends traffic to the dead IP until the JVM is restarted. The resolution: Configuring network address.cache.ttl. Disclaimer: always test code in a non-production environment. First, verify the environment. If this prints -1, your application is vulnerable to failover outages. If it prints a standard value like 30, the issue might be elsewhere. We explicitly set the cache TTL to 60 seconds. This balances network load against availability. AWS recommends a TTL of less than 60 seconds for RDS applications to ensure they respect the short TTL of Route 53 records during a failover event.
Follow-up 1. We set the DNS TTL to 60 seconds, but the app still connected to the old IP for 10 minutes. Why?
Answer: this is the connection pool factor. The DNS resolution happens only when a new connection is created. If your Hikari CP pool has minimum idle set high, it holds open established sockets to the old IP. You must ensure max lifetime in the pool is configured so connections are retired and re-established periodically, triggering a new DNS lookup.
Follow-up 2. Why does the JVM default to caching forever in some environments? What is the historical reason?
Answer: it is a legacy security feature related to DNS spoofing. If a security manager is present, the JVM assumes that DNS records should not change to prevent an attacker from hijacking a connection mid-session. In modern cloud environments where IP dynamism is a feature, not a bug, this default is harmful.
Follow-up 3. Curveball. We fixed the positive cache, but now if a service is briefly down in X domain, our app fails to reconnect for 10 seconds even after the service is back up. Why?
Answer: this is negative DNS caching. The JVM also caches failed lookups. The property network address.cache.negative.ttl controls this. If set too high, default is often 10 seconds. A momentary DNS blip becomes a 10-second hard outage for the application.
Scenario 9. The lazy initialization spike.
You deploy a Java Lambda function. The very first request, cold start, takes 8 to 10 seconds to complete, causing a PI gateway timeouts. However, all subsequent requests finish in 200 milliseconds. Increasing memory helps slightly, but the initial lag remains unacceptable.
Common assumptions.
Developers often assume Java is just slow on Lambda, or that the VPC network interface creation is the bottleneck. While VPC networking used to be slow, AWS Hyperplane ENIs fixed that years ago. The issue is usually inside the code structure.
The root cause. Lazy loading in the handler.
The latency is caused by lazy initialization logic placed inside the request handler method. When the code initializes an AWS SDK client, like S3 client, inside the handler one, the class loader must load all SDK classes heavy. 2. The SDK performs connection pooling setup and region discovery. 3. This happens during the customer request, billing the customer for the wait time. The resolution: static initialization, eager loading. Disclaimer: always test code in a non-production environment. We move the heavy object creation to a static variable. AWS Lambda allocates CPU bursts during the static initialization phase, the init phase. By doing the work here, we get more CPU power, and the initialized client is reused across all subsequent invocations. For Lambda, we replace the default Netty HTTP client, which is heavy and starts many threads, with the lighter URL connection HTTP client. This significantly reduces the class path scanning and startup time for short-lived functions.
Follow-up 1. We moved logic to static blocks, but cold starts are still around 3 seconds. How do we get this under 500 milliseconds without switching languages?
Answer: enable AWS Lambda Snap Start. Snap Start takes a snapshot of the initialized memory state after the static blocks run and caches it. When a new Lambda worker is needed, it restores the memory snapshot instead of running the initialization code, reducing cold starts by 90%.
Follow-up 2. Why does the first request after the cold start sometimes perform poorly before speeding up on the third or fourth request?
Answer: this is the JIT, just-in-time, compiler warming up. The JVM starts in interpreted mode. It takes a few executions for the C1 and C2 compilers to optimize the bytecode into native machine code. To mitigate this, we can use tiered compilation flags, XX colon plus tiered compilation XX colon tiered stop at level equals 1 to prioritize fast startup over long-term optimization.
Follow-up 3 curveball. You initialized your RDS database connection in the static block. Now, after the Lambda has been idle for 20 minutes, the first request fails with a connection closed error. Why?
Answer: static initialization is dangerous for stateful connections like JDBC. The Lambda container was frozen paused by AWS. During that freeze, the database server closed the idle connection. When the Lambda woke up, the static connection object was stale. For databases, you must check validity or reconnect inside the handler or use a proxy.
Scenario 10, the VPC endpoint ghost.
You are migrating a data-heavy workload to AWS ECS. The application needs to upload large files to S3. To save on NAT gateway data transfer costs, you configure a VPC gateway endpoint for S3. Immediately, uploads start timing out. Small metadata calls like list buckets work fine, but actual file transfers hang indefinitely. Security groups allow port 443.
Common assumptions.
Engineers usually blame S3 bucket policies or assume the VPC endpoint routing table is misconfigured. However, since small requests work, routing and permissions are actually correct. The issue is physical, not logical.
The root cause, MTU and MSS mismatch.
This is a black hole caused by packet fragmentation. EC2 instances supporting jumbo frames use an MTU maximum transmission unit of 9001 bytes. However, traffic passing through certain Docker interfaces or VPN tunnels is often capped at 1500 bytes. 1. The client sends a large packet, for example, 8000 bytes, with the Do Not Fragment DF flag set. 2. An intermediate hop like a Docker bridge accepts only 1500 bytes. 3. The hop drops the packet because it cannot fragment it. 4. The ICMP packet too big message, which tells the client to shrink the packet, is blocked by a security group. 5. The connection hangs. The resolution, TCP MSS clamping. Disclaimer: always test code in a non-production environment. We use tracepath, or pingm_size, to discover the path MTU. If you see the packet size drop suddenly from 9001 to 1500 at a specific hop, you have located the bottleneck. Instead of debugging every router in the path, we apply MSS clamping. This Iptable's rule modifies the TCP handshake, SYN packets. It effectively tells the application, even if you think you can send huge packets, clamp your segment size to the smallest path MTU discovered. This solves the hanging upload immediately.
Follow-up 1. Why did this work perfectly when we were using the NAT gateway, but failed when we switched to the VPC endpoint?
Answer: AWS NAT gateways automatically perform MSS clamping, source or destination check handling. They silently fix the packet size mismatch for you. VPC gateway endpoints are direct routes. They do not touch the packet headers, exposing the raw MTU mismatch between your jumbo frame EC2 instance and the Docker interface.
Follow-up 2. Changing Iptables on the host is not persistent in Fargate or managed Kubernetes. How do we fix this at the Docker level?
Answer: we must configure the Docker daemon itself. In the daemon.json file, we set the MTU 1500 property. This forces the Docker bridge network, Docker 0, to advertise a standard MTU, ensuring containers negotiate connections compatible with the outside world.
Follow-up 3 curveball. Why did I mention that the ICMP packet too big message was blocked? Why does that matter?
Answer: this is path MTU discovery, PMTUD. When a router drops a large packet, it tries to reply with an ICMP Type 3 code 4 message to tell the sender to shrink the packet. If your security group blocks inbound ICMP, your server never hears this warning and keeps resending the large packet, resulting in a permanent hang. Always allow ICMP Type 3 in your NACL.
Chapter 2 Summary.
We have navigated the deceptive world of the network. We diagnosed connection pools that freeze despite low load, API calls that vanish into black holes, DNS records that refuse to die, and packet sizes that physical networks cannot handle. These are the bugs that unit tests will never catch. But what happens when the network is fine, the memory is fine, but the data itself is corrupted? In the next chapter, we dive into the data layer. We will tackle database deadlocks, race conditions, and the hibernate N+1 nightmares that bring production systems to their knees. Next up, the data mystery.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem-solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Chapter 3, the data mystery.
We have fixed the JVM memory and stabilized the network layer. Now we face the most persistent and damaging class of production issues: data consistency and database performance. These are the bugs that do not just crash the app, they corrupt data and bring databases to their knees.
Database and consistency.
In this chapter, we explore the friction between Java's object model and the database's reality. We will diagnose DynamoDB hot partitions that defy auto-scaling, hibernate queries that accidentally DDoS your own database, and race conditions that silently overwrite user data.
Scenario 11. The DynamoDB throttling mystery.
You are running a high-traffic application backed by DynamoDB. To handle load spikes, you have enabled auto-scaling for both read and write capacity. However, during a marketing launch, your application starts failing with provisioned throughput exceeded exception. You check the console, and auto-scaling has indeed increased capacity, but the errors persist.
Common assumptions.
Developers often assume auto-scaling is simply too slow to react, lag time. They respond by manually setting the provisioned capacity to the maximum allowed, yet the throttling continues immediately.
The root cause, the hot partition.
Auto-scaling applies to the table level. However, DynamoDB stores data in distinct physical partitions shards. Each partition has a hard limit, typically 3000 RCUs/1000 WCUs. 1. Your schema design uses a low cardinality partition key, for example, tenant ID. 2. One specific tenant sends 90% of the traffic. 3. All that traffic hits a single physical partition. 4. That specific partition hits its hard limit, while the other 90% of the table's capacity sits idle. The resolution: right sharding, random suffixing. Disclaimer: always test code in a non-production environment. We implement right sharding. Instead of writing everything to tenant 123, we append a random suffix, 0 to 9. This forces the data to land on 10 different physical partitions, instantly increasing our write throughput capacity by 10 times. The partition key, PK, determines the physical location. By randomizing this key, we eliminate the hot key problem. The trade-off is that reading the data back requires querying all 10 shards, but for write-heavy workloads, this is the architecture standard.
Follow-up 1. We sharded the writes to solve throttling. How do we efficiently read all data for tenant 123 if it is now scattered across 10 random keys?
Answer: we must perform a scatter-gather query. The application must issue 10 parallel query requests, one for tenant 123 number 0, one for number 1, etc., and merge the results. This increases read complexity and cost, but is necessary to support the right scale.
Follow-up 2. Why did not we just switch the table to on-demand capacity mode? Would not that handle the burst automatically?
Answer: on-demand capacity handles table-level spikes instantly, but it does not remove the physical limits of a single partition. If a single key exceeds 1,000 WCUs or 3,000 RCUs, on-demand will still throttle. A hot key is a hot key, regardless of the billing model.
Follow-up 3. Curveball. The main table has plenty of capacity and the keys are well distributed. Yet, writes are still failing with throughput exceeded. You have a global secondary index, GSI. What is happening?
Answer: this is GSI backpressure. In DynamoDB, if a GSI is throttled because it lacks write capacity, the main table write will fail to ensure consistency. You might have a hot partition on the GSI partition key, even if the main table key is unique.
Scenario 12. The Hibernate N+1 nightmare.
You have a Spring Data JPA service. A simple API call get/users is triggered. The database CPU immediately spikes to 100%, and the request takes 5 seconds to complete. You check the code, and it is a simple user repository. Find all parentheses.
Common assumptions.
Developers often assume the database needs an index or that the instance type is too small. They scale up the RDS instance, but the CPU spike remains. They assume fetching 1,000 users should not be hard for a modern database.
The root cause, the N+1 select problem.
This is an ORM, object relational mapping, classic. You are fetching a list of users, but each user entity has a relationship, for example, @one-to-many list order. If the relationship is lazy default 1, Hibernate executes one query to get the 1,000 users. 2. As you serialize the response to JSON, the serializer touches user.getOrders parentheses. 3. Hibernate executes 1,000 separate queries, one per user, to fetch the orders. 4. Total queries 1,001. This floods the database. The resolution: join fetch. Disclaimer: always test code in a non-production environment. The standard selection only retrieves the user data. When the application accesses the associated orders list later, during JSON conversion, Hibernate is forced to go back to the database for every single user row. We change the query to use join fetch. This instructs Hibernate to execute a single SQL join query that retrieves both the user data and the order data in one go. The result is one query instead of 1,001, dropping database load by 99%.
Follow-up 1. We used join fetch and it fixed the N+1 problem, but now we get a warning in the logs, HHH000104, first result or max results specified with collection fetch, applying in memory. Why is this dangerous?
Answer: pagination and join fetch do not mix safely, because the SQL result set contains multiple rows per user. Due to the join, Hibernate cannot perform the limit or offset in the database. It fetches the entire dataset into the application memory and filters it there. This causes massive out-of-memory risks.
Follow-up 2. We have multiple use cases. Sometimes we need orders, sometimes we need addresses. Writing custom join fetch queries for every combination is unmaintainable. What is the cleaner solution?
Answer: use JPA entity graphs, @entity graph. This allows you to define declarative fetch plans. You can pass the graph name as a hint to the repository method, telling Hibernate exactly which relationships to eagerly load for that specific call without rewriting the query logic.
Follow-up 3. Curveball. You decided to fetch users their orders and their payments all in one join fetch query. Suddenly, the query returns millions of rows for just 100 users. Why?
Answer: this is the Cartesian product problem, multiple bag fetch exception. If a user has 50 orders and 50 payments, Hibernate creates a cross-product, 50/50 equals 2,500 rows per user. You should not fetch multiple independent collections in a single query. Use set instead of list, or fetch them in 2 separate queries.
Scenario 13, the SQS zombie message.
You have a worker service processing file exports triggered by SQS messages. The logs show the export completed successfully after 7 minutes. However, 5 minutes later, the exact same export triggers again. This loop continues until the message finally moves to the dead letter Q, DLQ. The logs show no errors, just repeated processing.
Common assumptions.
Developers often assume the code failed to delete the message after processing. They add extra logging to confirm the delete message call is made, but the duplication persists. They suspect an AWS bug or a producer sending duplicate messages.
The root cause, visibility timeout exceeded.
This is a configuration mismatch between the queue and the worker. SQS has a visibility timeout, default 30 seconds. 1. The worker picks up the message at t equals 0. 2. SQS makes the message invisible to other workers. 3. The worker takes 7 minutes to process the file. 4. At t equals 30 seconds or the configured timeout, SQS assumes the worker died because it has not heard back. 5. SQS makes the message visible again. 6. A second worker picks it up while the first is still running. The resolution, dynamic heart beating. Disclaimer, always test code in a non-production environment. For tasks with unpredictable durations, we cannot rely on a static timeout. We implement a heartbeat. A background thread repeatedly calls change message visibility while the main thread works. This tells SQS, I am still alive, please keep this message hidden from others. Once the heavy processing finally completes, we delete the message. Because we kept extending the visibility, no other worker was able to see or steal this message during the 7-minute window, ensuring exactly once processing, mostly.
Follow-up 1. Even with visibility timeouts configured correctly, SQS guarantees at least once delivery. How do we prevent corruption if a network error causes a true duplicate message?
Answer, we must make the consumer idempotent. We use a distinct key from the message, like order_ID, and check a dedicated transaction table, for example, DynamoDB, with a conditional write, put item if _not_ exists. If the write fails, we know we have already processed this order and silently discard the duplicate.
Follow-up 2. You are processing messages in batches of 10 to improve throughput. One message in the batch takes too long, triggering the visibility timeout. What happens to the other 9 completed messages?
Answer, if you do not explicitly delete the successful messages individually, the entire batch becomes visible again. SQS treats the batch as a unit for visibility. You must catch exceptions inside the batch loop and delete successful messages immediately, or the successful 9 will be reprocessed along with the failed one.
Follow-up 3 curveball. You switch to a FIFO to ensure ordering. Now, if a single message fails consumer-side processing, the entire queue stops moving. Why?
Answer, this is head-of-line blocking. In FIFOQs, AWS relies on message groups. If a message is not deleted or moved to DLQ, SQS will not deliver the next message in that group to preserve order. You must ensure your application handles failures by quickly moving bad messages to a DLQ or the entire partition halts.
Scenario 14. The race condition lost update.
You have an inventory system. User A reads a product stock as 10. User B reads the same product stock as 10. User A buys one item, updates stock to 9. Milliseconds later, user B buys one item, updates stock to 9. The database now shows 9, but 2 items were sold. The correct value should be 8. You lost a transaction.
Common assumptions.
Developers often assume that wrapping the code in @transactional prevents this. However, standard transaction isolation, read committed, does not prevent 2 transactions from reading the same initial state and overriding each other. Last write wins.
The root cause, lack of optimistic locking.
The database is doing exactly what it was told, update stock equals 9 where ID equals 1. Both transactions issued valid commands. The application lacks a mechanism to verify that the data has not changed since it was read. 1. T1 reads version 1. 2. T2 reads version 1. 3. T1 writes version 2. 4. T2 writes version 2, overriding T1's work. The resolution, JPA at version annotation. Disclaimer, Always test code in a non-production environment. We add a version field annotated with @version. JPA automatically manages this. Every time an update occurs, JPA increments the version number in the application memory before sending the query. The SQL changes drastically. It adds and version equals 1 to the where clause. If user B tries to update, the database sees the row is currently at version 2 from user A. The where clause fails version 1 equals version 2, the row is not updated, and JPA throws an optimistic lock exception.
Follow-up 1, we implemented @version, and now user B gets an exception instead of silent data loss. But this is a bad user experience. How do we handle optimistic lock exception?
Answer: we must implement a retry strategy. When the exception is caught, the application should automatically reload the fresh data from the database. Now stock equals 9. Reapply the business logic, 9 to 1 equals 8, and try the save again. This can be automated with the Spring @retriable annotation.
Follow-up 2, optimistic locking works great for low contention. But what if we have a flash sale where 10,000 users try to buy the same item at once? 9,999 retries will kill the DB.
Answer: for high contention, we switch to pessimistic locking. We use repository.find by ID lock mode type .pessimistic_right. This generates a select for update SQL query which locks the row at the database level. User B waits until user A finishes, rather than failing and retrying. It serializes access, preventing the retry storm.
Follow-up 3, curveball. Why not just use a native SQL atomic update, like update product set stock equals stock 1? Would not that avoid the versioning issue entirely?
Answer: yes. That is the most efficient solution for simple counters. However, it bypasses the JPA object lifecycle. You will not have the updated value in your Java object context immediately, and you lose the ability to validate invariants, for example, ensuring stock does not go below 0 inside the Java application logic before the write.
Scenario 15, the RDS connection storm.
You are running a successful flash sale. Your autoscaler creates 50 new containers to handle the traffic. Suddenly, your RDS database stops accepting new connections, throwing fatal, "Sorry, too many clients already." The CPU and memory on the database are fine.
Common assumptions.
Teams often rush to increase the max_connections parameter in the RDS parameter group. While this provides temporary relief, it consumes significant RAM per connection on the database host, eventually causing memory starvation.
The root cause, linear connection growth.
This is simple math working against you. In a microservices architecture, connections grow linearly with compute scaling. 1. Each container opens a pool of 10 connections, Hikari CP default. 2. You scale to 100 containers. 3. 100 containers, 10 connections equals 1,000 active database connections. 4. Most small to medium RDS instances cap out at roughly 500 to 700 connections. The resolution: RDS proxy connection multiplexing. Disclaimer: always test code in a non-production environment. We implement a AWS RDS proxy. This sits between your application and the database. Your application opens 1,000 connections to the proxy, which is designed to handle high concurrency. The proxy performs connection multiplexing. It reuses a small, efficient pool of actual database connections to serve the thousands of incoming requests. It rapidly switches the physical connection between applications, preventing the database from ever seeing the storm.
Follow-up 1, we implemented RDS proxy, but our monitoring shows pinning. The multiplexing efficiency has dropped to near 0. What is wrong?
Answer: pinning occurs when the proxy cannot safely reuse a connection. The most common cause is setting session state. If your code executes SET statement _timeout or uses prepared statements that are session scoped, the proxy must pin that client to a specific DB connection, disabling multiplexing. You must remove session-level configuration from your app logic.
Follow-up 2, aside from connection limits, what is the major resiliency benefit of using RDS proxy during a multi-AZ failover?
Answer: RDS proxy reduces failover downtime by up to 66%. Without the proxy, The Java DNS cache and TCP timeout settings delay reconnection. With the proxy, the application maintains its connection to the proxy, while the proxy internally handles the switch to the new writer instance instantly. The app never sees a connection refused error, just a momentary latency spike.
Follow-up 3 Curveball. RDS proxy adds an extra network hop. For a hyperlatency-sensitive trading application, is this recommended?
Answer: no. RDS proxy adds an average of 1 to 3 milliseconds of latency per query. For general web apps, this is negligible. For high-frequency trading where microseconds matter, you should manage the connection pool strictly within the application and avoid the proxy overhead.
Chapter 3 Summary.
We have solved the data mysteries. We fixed DynamoDB hot partitions with right sharding, silenced the Hibernate N+1 chatter with efficient fetching, resurrected zombie SQS messages with heartbeats, prevented race conditions with optimistic locking, and survived connection storms using RDS proxy. But what happens when the error is not in the database or the memory? What if the error is happening but the logs are silent? In the next chapter, we enter the world of observability. We will debug missing logs, broken distributed traces, and the high cost of logging too much. Next up, the needle in a haystack.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Chapter 4 The Needle in a Haystack, Logging and Tracing.
We have fixed the data and the network. Now we face the most terrifying scenario for an on-call engineer, the silent failure. The application claims to be healthy, but the transaction failed, and there are no logs. Or worse, the logs are so voluminous they are costing more than the infrastructure.
Distributed observability.
In a monolith, you could grep a single log file. In microservices, a single request jumps across 10 servers. Without precise correlation and propagation, debugging is impossible. In this chapter, we fix swallowed exceptions, broken distributed traces, and log buffering lag.
Scenario 16 The Missing Log Line.
A critical payment transaction fails. The customer support team sends you the order ID. You search CloudWatch logs, Splunk, or Datadog. You find the request received log and then silence. No completed, no error, no stack trace. The thread just seems to vanish.
Common assumptions.
Developers often assume the logging agent crashed or the thread died abruptly. OOM. However, if the container is still running, the issue is almost always in the code's error handling logic.
The root cause, swallowed exceptions.
The exception happened, but the code caught it and threw it away. This is the empty catch block anti-pattern. 1. The code catches exception too broad. 2. The catch block is empty or prints to system.out, which might be disabled. 3. The logging framework was not invoked with the exception object. The resolution, structured error logging. Disclaimer, always test code in a non-production environment. This is the crime scene. By catching a generic exception and doing nothing, or just printing a text string, the stack trace is destroyed. The observability system never knows an error occurred. We must pass the exception object E as the last argument to the logger. slf4j/log4j interprets this correctly and prints the full stack trace. Without this object, you get a log message, but no context on where it failed.
Follow-up 1. We fixed the catch blocks, but what if an unexpected runtime exception, like null pointer exception, happens outside our try-catch logic? It still vanishes.
Answer, we must register a thread.uncaught_exception handler globally, or use a framework-specific handler, like Spring's @controller advice for web, or a sync_uncaught_exception handler for @async methods. This acts as the final safety net to log anything that bubbles to the top.
Follow-up 2. The logs show the application starting up, and then immediately stopping with process finished with exit code 0. No errors. What happened?
Answer, a library or dependency likely called system.exit 0. This shuts down the JVM immediately. Security libraries or older CLI frameworks sometimes do this upon validation failure. To debug, you can use a Java security manager, deprecated but useful here, to forbid system.exit and force it to throw an exception instead.
Follow-up 3. Curveball. You are logging the error correctly, but it still does not show up in CloudWatch. The app is running in a Docker container. Why?
Answer, the log appender is writing to a file inside the container, not to stdout standard output. In containerized environments, ECS or EKS, you must configure your logback.xml to use console appender. If logs go to a file, and the file is not rotated or tailed by a sidecar, they die with the container.
Scenario 17. The X-ray trace break.
You are using a AWS X-ray for distributed tracing. You see the trace for service A. You see the trace for service B. But they are two separate traces. The graph shows them as disconnected, making it impossible to measure the total end-to-end latency of a user request.
Common assumptions.
Developers assume that simply adding the X-ray dependency is enough. They think the agent running on the EC2 instance automatically stitches everything together. It does not.
The root cause, missing context propagation.
Distributed tracing works by passing a trace ID in the HTTP headers. For example, exams and trace ID from service A to service B. If your HTTP client is not configured to inject this header, the chain breaks. 1. Service A receives a request and starts a trace segment. 2. Service A calls service B using a standard HTTP client. 3. The HTTP client sends the request without the trace header. 4. Service B sees a request with no header and starts a brand new, unrelated trace. The resolution, instrumentation interceptors. Disclaimer, always test code in a non-production environment. For AWS services, like DynamoDB or SQS, we must register the tracing interceptor. This intercepts every outgoing request, grabs the current thread's trace ID, and injects it into the AWS-specific headers so the downstream service can continue the graph. For generic HTTP calls to other microservices, we must add a client interceptor. This does the same job. It modifies the HTTP headers of the outgoing GET or POST request to include the exams and trace ID, ensuring service B knows it is part of service A's transaction.
Follow-up 1. We instrumented the client, but when we use @async or a background thread, the trace still breaks or disappears. Why?
Answer, a AWS X-ray stores the trace context in a thread local. When you spawn a new thread, that thread local is empty. You must manually pass the entity segment to the new thread using OSC's ray.setTraceEntity, parent entity, inside the runnable.
Follow-up 2. Tracing is working, but our X-ray bill is astronomical. We do not need to trace 100% of traffic. How do we fix this without changing code?
Answer, we configure sampling rules in the X-ray console or the sidecar configuration xraydaemon.yaml. We can set a fixed rate, for example, 5%, or a reservoir, for example, first one requests per second. This reduces data volume and cost while still providing statistical visibility.
Follow-up 3 curveball, you are using SQS. Service A sends a message. Service B consumes it. The trace map shows A and B, but they are not connected by a line. Why?
Answer: SQS is asynchronous. X-ray treats the send and the consume as separate logical transactions if not explicitly linked. In the consumer, you must extract the trace header from the SQS message attributes, system attribute AWS trace header, and manually start a new segment linking back to that parent ID.
Scenario 18, the log aggregation lag.
You deploy a fix to production. You are watching the logs in CloudWatch or Splunk to verify it. You see traffic hitting the load balancer, but the application logs are empty. 5 minutes later, a massive chunk of logs appears all at once. This latency makes real-time debugging impossible.
Common assumptions.
Engineers often blame the logging agent, CloudWatch agent, or FluentBit for being slow. They restart the agent, but the lag persists. The issue is usually upstream, inside the application's buffer.
The root cause, buffer flushing strategy.
To improve performance, logging frameworks logback/log4j2 and agents buffer logs in memory before sending them over the network. 1. The buffer fills up slowly during low traffic. 2. The flush interval is set too high, for example, 60 seconds. 3. Logs sit in RAM until either the buffer is full or the timer expires. The resolution, tuning the appender. Disclaimer: always test code in a non-production environment. For real-time debugging, a massive queue is detrimental. We size the queue to handle bursts, but not so large that it holds minutes worth of logs. If the agent FluentBit is configured, we also check its flush_interval setting, reducing it to 1 to 5 seconds. This is critical for stability. If the logging backend, CloudWatch, is slow and the buffer fills up, the default behavior is to block the application threads until space clears. By setting never block to true, we choose to drop log lines rather than freeze the application.
Follow-up 1, we reduced the flush interval to 1 second, but now the CPU usage of the logging sidecar has tripled. Why?
Answer: sending logs in tiny batches requires more network calls and serialization overhead. It is a trade-off. For real-time debugging, we pay in CPU. For archive logging, we prefer large batches and compression. A balanced approach is 5 to 10 seconds.
Follow-up 2, the logs are arriving instantly now, but stack traces are broken. The exception header is in one log event, and the stack lines are in separate disconnected events. Why?
Answer: this is a multi-line parsing issue. The log agent reads line by line. It sees a new line in the stack trace and thinks it is a new log entry. You must configure the Docker log driver or FluentBit with a multi-line parser, regex, that detects the start of a log line, for example, a timestamp, and groups indented lines with the previous one.
Follow-up 3 curveball, logs work fine, but when the pod restarts, we consistently lose the last 10 seconds of logs, often the critical error that caused the crash. How do we fix this?
Answer: the application is shutting down faster than the logger can flush. We need to add a shutdown hook delay. In logback, set shutdown hook class equals ch.qos.logback.core.hook.delaying shutdown hook /. This forces the JVM to wait, for example, 5 seconds during termination, giving the async appender time to drain its buffer to stdout.
Scenario 19, the correlation ID void.
You are debugging a failed transaction in a microservices mesh. You find an error in service C. You want to know which user request in service A triggered this. However, the logs in service C only show internal server error. There is no shared ID to link it back to the ingress request.
Common assumptions.
Developers often search by timestamps, hoping to match requests by time. In a high-traffic system, this is impossible as hundreds of requests occur per second. Without a unique identifier passed through the chain, the context is lost.
The root cause, missing MDC propagation.
Logging frameworks use the MDC map diagnostic context to attach metadata to a thread. If you do not explicitly extract the correlation ID from the incoming request and put it into the MDC, your logs will be anonymous. 1. Service A generates a UUID. 2. Service A calls service B but does not pass the UUID in headers. 3. Service B receives the call but does not look for a header. 4. The chain is broken. The resolution, MDC filter and header injection. Disclaimer, always test code in a non-production environment. This pattern ensures continuity. If an upstream service sent an ID, we use it. If we are the edge service, we generate it. This creates a single golden thread ID that persists across the entire distributed transaction. We place the ID into the mapped diagnostic context, MDC. The logging framework automatically grabs this value and adds it to every log line. For example, info correlation ID equals ABC 123 processing payment. We do not need to manually add it to every log.info parentheses call.
Follow-up 1. We added the code to populate the MDC, but the correlation ID still is not showing up in the text of the log file. What did we miss?
Answer, we missed the pattern layout in logback.xml. Populating the MDC is only half the battle. You must tell the appender to print it. You need to add %x correlation ID to your encoder pattern, pattern %d%, 5-level %x correlation, ID %, in /pattern.
Follow-up 2. The filter works for the main request thread. But when we start to add a sync task or use a completable future, the correlation ID disappears from the logs of the async task. Why?
Answer, MDC is thread local. Child threads do not inherit MDC context from parents by default. You must use a task decorator in Spring or wrap your runnable to copy the MDC.getCopyOfContext map parentheses from the parent thread, and MDC.setContextMap parentheses in the child thread before execution.
Follow-up 3. Curveball. You are passing X correlation ID correctly, but Nginx or the load balancer is dropping it before it reaches your app. Why?
Answer, some load balancers or WAF sanitize headers. If your header name contains underscores, for example, X_correlation_ID, Nginx defaults to dropping it __in_ headers off. Always use hyphens in custom HTTP headers to ensure compatibility.
Scenario 20. The too much info cost.
Your application is stable, but your CFO is angry. The CloudWatch logs bill has surpassed the EC2 bill. You investigate and find terabytes of logs being ingested. The application is logging the full payload of every HTTP request and response for debugging purposes.
Common assumptions.
The team argues they cannot turn off the logs because we might need them if something breaks. They leave debug logging enabled in production just in case, treating logs as a data dump rather than a signal.
The root cause, static log levels.
The architecture lacks the ability to change verbosity dynamically. To debug a specific issue, developers set the global level to debug and leave it there because redeploying to switch back to info is too disruptive. 1. Logging full JSON payloads in the happy path. 2. Logging inside high-frequency loops. 3. Lack of sampling or filtering. The resolution, dynamic logging Spring Boot actuator. Disclaimer, always test code in a non-production environment. We enable the Spring Boot actuator loggers endpoint. This exposes an API that allows us to inspect and modify the log configuration of the running application without a restart. Now we run the application at info level by default, saving money. When a specific issue arises, we use this API to switch only that specific package to debug for 10 minutes to capture the evidence, and then switch it back. We get the data we need without the permanent cost penalty.
Follow-up 1. Exposing the /actuator or loggers endpoint to the public internet is a security risk. How do we secure this powerful tool?
Answer, we must protect it with Spring Security. We restrict access to the actuator endpoints to a specific ops role, or better yet, we put the actuator on a different port, management.server.port equals 8081, and configure the load balancer or ingress to block external access to port 8081. Making it accessible only from the internal VPN.
Follow-up 2. We need payload logging for audit, but not for everything. How do we log 100% of errors, but only 1% of successful requests?
Answer, we implement head-based sampling in our logging filter. We generate a random number 1 to 100. If it is equals 1, we log the success payload. If an exception is thrown, we force logging regardless of the random number. This gives us full visibility into failures while reducing happy path noise by 99%.
Follow-up 3. Curveball. Even at info level, we accidentally logged a customer's credit card number in an exception message. It is now in CloudWatch. What is the immediate remediation?
Answer: this is a data leak. First, rotate the compromised credentials, if any, and trigger your incident response plan. Technically, you cannot delete individual log lines from CloudWatch. You may have to delete the entire log stream or expire the log group. To prevent recurrence, implement a masking pattern layout in Logback that uses regex to replace credit card patterns, like \D4\D4\D4\D4, with before the log is written.
Chapter 4 Summary.
We have illuminated the black box. We prevented exceptions from being swallowed, stitched together distributed traces across boundaries, optimized log buffering for real-time visibility, ensured logs are traceable via correlation IDs, and implemented dynamic log levels to balance cost with insight. Now that we can see what is happening, we need to master the tools that allow us to interact with the AWS cloud. In the next chapter, we dive into the AWS SDK itself. We will solve S3 memory crashes, DynamoDB pagination loops, and thread pool exhaustion. Next up, advanced AWS SDK and libraries.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Chapter 5 Advanced AWS SDK and Libraries.
We have secured the infrastructure and the data. Now we look at the code that connects them. The AWS SDK for Java is powerful, but it assumes you understand its internal buffering, pagination, and threading models. Misusing these libraries is the fastest way to trigger out-of-memory errors and throttling exceptions at scale.
Scenario 21. The S3 multipart upload memory crash.
You need to upload a large generated report, 5 gigabytes to S3. You write a simple service to generate the file and upload it. It works for 100 megabytes files in testing. But in production, as soon as the 5 gigabytes upload begins, the container crashes with java.lang. Out-of-memory error, Java heap space.
Common assumptions.
Developers often assume they need a larger heap. They bump XMX to 8 gigabytes. It works once, but crashes again when 2 users upload simultaneously. They assume S3 is slow and holding onto memory.
The root cause, buffering in memory.
The issue is how the data is passed to the SDK. If you read the entire file into a byte array or use a standard put object request without a file stream, the SDK or your code loads the entire 5 gigabytes into RAM before sending the first packet. 1. Naive implementation, files.read all bytes, path loads 5 gigabytes into heap. 2. Standard put object requires content length. If using an input stream without length, the SDK might buffer it to calculate size. 3. Result: 2 concurrent uploads consume 10 gigabytes RAM. The resolution: S3 Transfer Manager streaming. Disclaimer: always test code in a non-production environment. This line is the killer. Read all bytes allocates a contiguous byte array in the heap matching the file size. This is impossible to scale. We use the AWS CRT-based S3 Transfer Manager. By pointing it to the path on disk, the SDK streams the data in small chunks, multi-part upload. It only keeps a few megabytes in RAM at any time, allowing a 512 megabytes container to upload a 1 terabytes file successfully.
Follow-up 1. The multi-part upload failed halfway due to a network cut. We retried and succeeded, but now our S3 storage bill is double what it should be. Why?
Answer: this is the incomplete multi-part upload trap. When a multi-part upload fails, the parts that were uploaded stay in S3 in a hidden state, costing money for storage. They do not appear in the standard file listing. You must configure an S3 lifecycle policy to delete incomplete multi-part uploads after days.
Follow-up 2. For compliance, we need to guarantee the file on S3 is bit-for-bit identical to the local file. S3 eTag is not a simple MD5 for multi-part uploads. How do we verify integrity?
Answer: we must use additional checksums. In the SDK v2, we enable checksum algorithm, checksum-algorithm.SHA-256. The SDK calculates the SHA-256 on the fly during upload and sends it to S3. S3 verifies it upon receipt and stores it as metadata. We can then verify this checksum after the upload completes.
Follow-up 3. Curveball. You switch to S3 Transfer Manager, but now the application crashes on startup with unsatisfied link error. It works on your Mac, but fails on Alpine Linux in Docker. Why?
Answer: the S3 Transfer Manager relies on the AWS CRT common runtime, which uses native code clibs for performance. Alpine Linux uses muscle lib, while standard builds often target glib. You must include the specific AWS CRT client dependency classifier for Linux muscle or switch to a Debian/UBI-based container image.
Scenario 22. The DynamoDB pagination loop.
You write a background job to scan a DynamoDB table and archive old records. The table has 10 million items. Your code runs, finishes quickly, and reports success. But when you check the archive, only about 10,000 records were processed. The job missed 99% of the data.
Common assumptions.
Developers assume that calling dynamodb.scan parentheses returns all records matching the filter. They treat it like a JDBC select, expecting the SDK to handle the heavy lifting of fetching all rows.
The root cause: 1 megabytes page limit.
DynamoDB API has a hard limit. A single scan or query response cannot exceed 1 megabytes of data. 1. The SDK makes one call. 2. DynamoDB reads 1 megabytes of data, approx 100 to 1,000 items. 3. It returns that page along with a last evaluated key. 4. If the code ignores this key and does not loop, it stops after the first page. The resolution: do-while pagination loop. Disclaimer: always test code in a non-production environment. This is the engine of pagination. On the first iteration, last key is null, so it starts at the beginning. On subsequent loops, we pass the key we got from the previous response, telling DynamoDB to start reading after this record. We must loop until last evaluated key is null. Null means end of table. If we do not check this, we are silently dropping data. Note: even if response.items parentheses is empty, last evaluated key might not be null if the scan 1 megabytes contained filtered out data, so checking the key is the only reliable stop condition.
Follow-up 1. Writing this do-while loop for every query is boilerplate heavy and error-prone. Does the AWS SDK v2 offer a cleaner way?
Answer: yes. Use the DynamoDB enhanced client or the paginator methods, for example, scan paginator. These provide an iterable interface. You can simply perform for page p client.scanPaginator, rec, and the SDK handles the token swapping and looping internally.
Follow-up 2. Scanning a 100 gigabytes table sequentially is taking 24 hours. We have plenty of read capacity, RCU. How do we speed this up?
Answer, use a parallel scan. You divide the scan into segments, for example, 20 segments. You spawn 20 threads. Each thread calls scan with total segments equals 20 and segment equals X. DynamoDB divides the table physically and reads from 20 locations simultaneously, increasing throughput by nearly 20 times.
Follow-up 3 Curveball. You are using pagination correctly, but users report that sometimes an item they just added does not appear in the query results immediately. Why?
Answer, DynamoDB queries are eventually consistent by default to save RCU. It might take a second for a write to propagate to all storage nodes. To fix this, you must explicitly set consistent read true in your query request, which consumes 2 times the read capacity units but guarantees the latest data.
Scenario 23. The SQS batch delete error.
Your application consumes SQS messages in batches of 10 to improve throughput. Occasionally, one message in the batch contains malformed data and throws an exception. You catch the exception and throw it to trigger a retry. However, this causes the entire batch of 10 messages, including the 9 successful ones, to reappear in the queue.
Common assumptions.
Developers assume SQS knows which specific message failed. They think throwing an exception marks only the current message as failed. But SQS visibility is binary for the request context. Either the batch succeeded or it did not.
The root cause, partial batch failure.
When you pull a batch of messages, their visibility timers start together. If you throw an exception that prevents the explicit deletion of the batch one, you fail to call delete message batch for the successful ones. 2. The visibility timeout expires for all messages in the batch. 3. SQS redelivers all 10 messages. 4. The 9 good messages are processed again, duplicate processing. 5. The 1 bad message fails again, repeating the loop. The resolution, explicit partial deletion. Disclaimer, always test code in a non-production environment. We wrap the processing of each message in its own try-catch block. If one fails, we log it, but we do not throw the exception up to the main loop. By suppressing the exception, we allow the loop to continue and process the remaining 9 messages. At the end, we send a batch delete request containing only the messages that succeeded. The failed message is left untouched. Its visibility timeout will expire, and SQS will redeliver only that specific message to a future worker.
Follow-up 1. This manual deletion is tedious. If I am using a WS Lambda with SQS event source, is there a better way?
Answer, yes. Enable report batch item failures in the Lambda trigger configuration. Then in your code, return a specific JSON response batch item failures, item identifier, ID underscore of underscore failed underscore MSG. A WS Lambda will read this, delete the successes, and retry only the IDs you listed.
Follow-up 2. The bad message keeps failing and retrying forever, clogging the logs. How do we remove it automatically?
Answer, configure a dead letter queue, DLQ, with a max receive count, for example, 5. After the message has been delivered and failed 5 times, SQS will automatically move it to the DLQ. This isolates the poison pill for manual investigation without blocking the main queue.
Follow-up 3 Curveball. Your code calls delete message batch successfully, but one of the IDs in the request fails to delete with an internal failure. What should you do?
Answer, the delete message batch API returns a list of successful and failed entries. You must check the failed list in the response. If SQS failed to delete a message, rare but happens, you should log it or retry the delete. Otherwise, that successful message will be redelivered, causing a duplicate transaction.
Scenario 24. The parameter store throttling.
Your application fetches its database password and API keys from a WS SSM parameter store. It works fine in staging. In production, under high load, the application starts crashing with throttling exception from the SSM API. The AWS console confirms you are hitting the API limits.
Common assumptions.
The team assumes they need to request a quota increase from AWS support. While possible, the default throughput is actually quite high, 3,000 rec per sec for higher tiers. Hitting this limit usually implies a fundamental architectural flaw.
The root cause, zero caching.
The code is calling SSM client.get parameter parentheses inside the critical request path. For example, every time a user logs in. 1. 10,000 users log in per minute. 2. 10,000 API calls are made to SSM. 3. This is slow network latency and expensive API costs. 4. It triggers the AWS throttling governor. The resolution, client-side caching with TTL. Disclaimer, always test code in a non-production environment. We wrap the SSM call in a cache with a time to live, TTL. Instead of calling AWS every time, we call it once. The value is stored in the JVM memory for 5 minutes. Subsequent calls during that window are instant. This dramatically reduces API volume. Even if traffic spikes to 100,000 RPS, the SSM API only sees one request every 5 minutes. This eliminates throttling and removes network latency from the user login flow.
Follow-up 1. We implemented caching, but now we have to wait 5 minutes for config changes to go live. We need faster updates without polling. What is the AWS native solution?
Answer: use AWS app config. It runs a sidecar agent on your EC2/container. The agent polls AWS for changes and caches them locally on localhost. Your app just requests the config from the local agent. This gives you instant access with zero latency, while AWS manages the polling optimization.
Follow-up 2. We are caching secure string parameters. Does this introduce a security risk?
Answer: yes, slightly. The decrypted secret is now sitting in the Java heap string pool for 5 minutes. If someone captures a heap dump, they can see the password. To mitigate this, ensure heap dump generation is restricted, or if extremely sensitive, minimize the TTL or use a sealed object approach to decrypt only at the exact moment of use.
Follow-up 3. Curveball. Why use SSM parameter store for database passwords instead of AWS Secrets Manager? When would you switch?
Answer: SSM is cheaper free for standard throughput and simpler for static config. Secrets Manager is specifically designed for credentials. It supports automatic rotation, changing the DB password every 30 days. If your compliance policy requires password rotation, you must use Secrets Manager, not SSM.
Scenario 25. The fork join pool deadlock.
You optimize your data processing job by using Java parallel streams, list.parallelstream parentheses .map. It works great in dev. In production, the entire application starts stalling. Health checks fail, and even unrelated parts of the app, like simple event processing, become incredibly slow.
Common assumptions.
Developers assume that parallel stream parentheses creates new threads for the task. They do not realize it shares a global resource. They assume the slowdown is due to CPU exhaustion, but CPU metrics often show low utilization with high wait times.
The root cause, common pool contention.
All parallel streams in a JVM share the same fork join pool. Common pool parentheses. The size of this pool is CPU cores 1. 1. Your container has 2 vCPUs. The pool has 1 thread. 2. You run an S3 upload blocking I or O inside a parallel stream. 3. That 1 thread gets blocked waiting for S3. 4. All other parallel streams in the entire JVM are now queued, waiting for that 1 thread to free up. 5. The app deadlocks. The resolution, custom thread pools. Disclaimer: always test code in a non-production environment. We isolate the heavy work. By submitting the parallel stream task to a custom fork join pool, we force the stream to use the threads from that pool instead of the global common pool. If these threads block, they do not affect the rest of the application. For I or O operations, like calling AWS, parallel streams are actually a poor choice. Completable future with a dedicated executor service is superior. It allows precise control over concurrency, for example, 20 parallel uploads, independent of CPU core count.
Follow-up 1. When is parallel stream parentheses actually the right choice?
Answer: it is perfect for CPU-bound tasks in memory, such as calculating a hash for a list of strings or sorting complex objects. It is designed to utilize all CPU cores fully. Just never use it for blocking operations like database or API calls.
Follow-up 2. Why did this deadlock happen on the 2V CPU container, but not on my 8-core laptop?
Answer: on your 8-core laptop, the common pool has 7 threads. If you block one, you still have 6 left to process health checks and other tasks. On a 2-core container, the pool has 1 thread. Blocking it stops the world. Container constraints expose concurrency bugs that development machines hide.
Follow-up 3. Curveball. When we switched to completable future, our logs lost the transaction ID. Why?
Answer: as discussed in Chapter 4, completable future spawns tasks on new threads. The MDC context, thread local, is not copied automatically. You must manually extract the context map, mdc.getCopy of context map parentheses, and pass it to the async task to restore it, mdc.setContextMap parentheses, before execution begins.
Chapter 5 Summary.
We have mastered the SDK. We learned to stream S3 uploads to save RAM, handle DynamoDB pagination correctly, manage SQS partial batch failures, cache SSM parameters to prevent throttling, and isolate thread pools to prevent deadlocks. In the final chapter, we look at the weirdest, hardest to diagnose issues, the ones that happen only at midnight or only when you aren't looking. We will debug midnight CPU spikes, log rotation deadlocks, and Kinesis iterator expirations. Next up, production war stories.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Chapter 6 Production War Stories.
We have arrived at the final frontier. These are the edge cases, the bugs that do not happen during the day when you are watching the dashboard. They happen at midnight. They happen when a specific file size is hit. They happen when 2 services talk to each other in a specific order. These are the war stories.
Scenario 26. The midnight CPU spike.
Every night at exactly 00 to 00 UTC, your production fleet triggers a high CPU alarm. The CPU hits 100% for 2 minutes, causing latency spikes for international users. There is no scheduled cron job in your application code, and traffic is low at that hour.
Common assumptions.
Engineers look for a scheduled task in Spring but find nothing. They assume AWS is doing underlying maintenance or that a backup job is running, but the database metrics are flat.
The root cause, log rotation compression.
The issue is infrastructure management, not application logic. You are writing logs to a file, for example, app.log. The logging framework logback or the system tool logrotate is configured to rotate and compress these logs at midnight. 1. At 00 to 00, the log file, often gigabytes in size, is rotated. 2. The system begins gzip compression on the old file. 3. Gzip is extremely CPU intensive. 4. On a small container, for example, 1 vCPU. This background task steals 100% of the processor cycles from the Java application. The resolution, delay or offload compression. Disclaimer, always test code in a non-production environment. If your file pattern ends in GZ, logback will attempt to compress the file immediately upon rotation within the JVM process. For large files, this is a performance killer. We remove the GZ extension. We let the JVM simply rename the file, which is instant. We then configure an external process, like a sidecar, to compress old logs using nice N19 gzip, which ensures the compression only uses spare CPU cycles and yields to the application.
Follow-up 1. If we use the Linux logrotate tool instead of logback, how do we prevent the spike?
Answer, use the delay compress option in your logrotate.conf. This rotates the file today but postpones compression until the next rotation cycle, tomorrow. This means you are compressing yesterday's file, which is not being written to, avoiding I or O contention, though CPU contention remains unless you use nice.
Follow-up 2. It is not CPU, it is disk I/O. The compression is consuming all IOPS input or output operations per second, causing the database on the same host to slow down. How do we fix this?
Answer, this is why we treat servers as cattle, not pets. In modern cloud architecture, you should not be logging to local disk at all if possible. Use a standard output, stdout, driver that streams logs directly to a collector like Fluent, which sends them to S3 or CloudWatch asynchronously. Remove local disk I/O contention entirely.
Follow-up 3. Curveball. Why did the spike happen at 00 to 00 UTC when our servers are in New York, EST?
Answer, servers should always run in UTC to avoid daylight saving time bugs. However, if your traffic peak is actually at 7 p.m. EST, 00 to 00 UTC, you should configure the rotation time to be during your business low traffic window, for example, 04 to 00 UTC, rather than the default midnight.
Scenario 27. The deadlocked logger.
Your application stops processing requests. It is not crashing, it is just hanging. You capture a thread dump. You see dozens of threads stuck in blocked state. Surprisingly, they are all blocked inside a logging call, ch.qos.logback.core.output stream appender.write bytes.
Common assumptions.
Developers assume logging is free and safe. They suspect a database lock. They rarely suspect that the simple act of writing log.info parentheses can freeze the entire application.
The root cause, synchronous blocking I or O.
Standard file appenders are synchronous. When you call log.info, the application thread locks the appender and waits for the disk write to complete. 1. The disk EBS volume experiences a latency spike or runs out of burst credits. 2. Thread A calls log.info and blocks waiting for disk. 3. Thread A holds the lock on the logger. 4. Thread B, C, and D call log.info and get blocked waiting for the lock. 5. The entire application grinds to a halt. The resolution, async appender. Disclaimer, always test code in a non-production environment. We wrap the blocking file appender inside an async appender. When the application calls log.info, it now simply places the message into an in-memory queue and returns immediately. A separate background thread handles the slow disk I/O. We update the root logger to use the async appender. This decouples application throughput from disk latency. Even if the disk stalls for 1 second, the application threads continue processing user requests without pausing.
Follow-up 1. Async logging is fast, but what is the risk if the application crashes abruptly, for example, kill -9?
Answer, data loss. Because logs are buffered in memory, the queue. If the JVM is killed instantly, the logs in the queue are never written to disk. For audit-critical transaction logs, we might prefer synchronous logging to guarantee durability, accepting the performance penalty.
Follow-up 2. We switch to async appender, but we still see some contention. Is there a faster option than logback?
Answer, yes. Log4j2 using the LMAX disruptor. Log4j2's asynchronous loggers use a lock-free interthread messaging library, disruptor, instead of a standard array blocking queue. This provides significantly higher throughput and lower latency than Logback's async appender.
Follow-up 3 curveball. We are logging to console standard out, not a file. Can this still block?
Answer: yes. System.out is synchronized. In a high-throughput Docker container, the pipe connecting standard out to the logging driver, for example, JSON file auslogs, has a buffer. If the driver is slow to read, the buffer fills, and system.out.println will block the application thread. Async logging is recommended for console output too.
Scenario 28. The Kinesis shard iterator expired.
You have a Kinesis consumer application. It works fine for small messages. Suddenly, you receive a batch of complex data. The application processes a few records and then throws expired iterator exception. It refetches the batch, processes the same few records, and fails again. It is stuck in an infinite loop.
Common assumptions.
Developers assume the Kinesis service is erroring out. They verify the stream status is active. They do not realize the error is coming from their own processing speed relative to the Kinesis timeout contract.
The root cause, slow processing.
When you get a batch of records from Kinesis, you get a shard iterator. This iterator is valid for exactly 5 minutes 300 seconds. 1. You fetch 100 records. 2. Your processing logic takes 4 seconds per record. 3. Total time equals 400 seconds. 4. When you try to checkpoint or fetch the next batch, 5 minutes have passed. 5. The iterator is expired. The checkpoint fails. 6. The KCL, Kinesis Client Library, restarts the batch from the beginning. The resolution, tuning batch size and parallelism. Disclaimer: always test code in a non-production environment. We reduce the max records limit in the consumer configuration. By fetching smaller batches, for example, 50 instead of 1,000, we ensure that even if processing is slow, the entire batch finishes well within the 5-minute window. We switch from sequential processing, for each, to parallel processing, parallel stream, or executor service. This utilizes all CPU cores to crunch the batch faster, significantly reducing total wall clock time.
Follow-up 1. We processed 49 out of 50 records successfully, but the 50th failed. If we do not checkpoint, we replay all 50. How do we handle this?
Answer: you must catch the exception for the 50th record, log it, and optionally send it to a dead letter queue (DLQ). Then, you must checkpoint successfully. Kinesis does not support individual record acknowledgement. You commit the batch cursor, implying I have handled everything up to here.
Follow-up 2. We are receiving provision throughput exceeded on the consumer side. We thought that error was only for producers. Why?
Answer: a Kinesis shard supports 2 megabytes per sec read throughput. If you have 5 different applications, consumer groups, reading from the same stream, they share that 2 megabytes limit. If they all read at once, they throttle each other. The fix is to use enhanced fanout, which gives each consumer its own dedicated 2 megabytes per sec pipe.
Follow-up 3 curveball. We switched to parallel processing to speed up. Now our data is corrupted because order updates are being processed before order creation. Why?
Answer: parallel processing breaks ordering guarantees within the batch. Kinesis guarantees order per shard key. If record 1 create and record 2 update for the same user are in the same batch, and thread B processes record 2 faster than thread A processes record 1, you fail. For ordered data, you must process sequentially or shard logically.
Scenario 29. The lambda/TMP space issue.
You have a Lambda function that generates PDF reports. It works perfectly for weeks. Suddenly, it starts failing with I/O exception, no space left on device. You check the PDF size. It is only 5 megabytes. The lambda/TMP directory limit is 512 megabytes or up to 10 gigabytes now. Why is it full?
Common assumptions.
Developers assume that when a Lambda execution finishes, the environment is wiped clean. They treat /TMP as ephemeral storage that auto-deletes after the function returns.
The root cause, container reuse.
AWS Lambda reuses the same execution environment container for subsequent requests to improve performance. Warm starts. 1. Request 1 writes report 123.pdf to /TMP. 2. Request 1 finishes but does not delete the file. 3. The container freezes. 4. Request 2 wakes up the same container. /TMP still contains report 123.pdf. 5. After 100 requests, /TMP is full. The resolution, explicit cleanup in finally block. Disclaimer, always test code in a non-production environment. We wrap the logic in a try finally block. The finally block runs whether the upload succeeded or through an exception. We explicitly delete the temporary file. This ensures that the disk state is reset for the next invocation, keeping the container healthy indefinitely.
Follow-up 1. We genuinely need more than 512 megabytes for video processing. What is the configuration fix?
Answer: AWS Lambda now allows you to configure ephemeral storage, /TMP, size up to 10 gigabytes. You can increase this setting in the Lambda configuration console or Terraform. Ephemeral_storage size equals 10,240.
Follow-up 2. Besides disk space, what is the major security risk of leaving files in /TMP?
Answer: data leakage. If request a write-sensitive user data, for example, a tax form, to /TMP and does not delete it, and request B, serving a different user, runs in the same container, a vulnerability in your code like directory traversal could allow user B to read user A's file. Always clean up.
Follow-up 3. Curveball. It is not the disk filling up, it is the memory. We see out-of-memory error after 100 invocations, but only when we use a static list cache. Why?
Answer: static variables persist across invocations in the same container. If you keep adding items to a private static list string history without ever clearing it, it will grow indefinitely until the container crashes. You must manage the lifecycle of static caches, or use a proper caching library like Guava with size eviction.
Scenario 30. The distributed deadlock.
You have two microservices, Service A and Service B. Service A calls Service B synchronously. To complete the request, Service B calls Service A back synchronously to fetch some user details. Under low load, this works. Under high load, both services time out and the system locks up.
Common assumptions.
Developers assume they just need more threads. They scale up the thread pools on both services. It takes slightly longer to fail, but it still locks up. They assume it is a network loop.
The root cause: circular dependency resource starvation.
This is a classic distributed deadlock. 1. Service A has 10 threads, all 10 are busy calling Service B. 2. Service A has 0 threads left to handle incoming requests. 3. Service B receives the calls. To finish, it tries to call Service A. 4. Service A cannot accept the call, 0 threads free. 5. Service B waits. Service A waits for Service B. 6. Deadlock. The resolution: architectural refactor async. Disclaimer: always test code in a non-production environment. We break the temporal coupling. Service A sends a message to a queue and immediately frees up its HTTP thread. It does not wait for B. Service A is now available to handle other requests. Service B picks up the message later. If it calls Service A has plenty of free threads to respond. By making the initial trigger asynchronous, we prevent the resource hold and wait condition required for a deadlock.
Follow-up 1. If we cannot refactor to async immediately, how do we temporarily mitigate this with timeouts?
Answer: we must ensure read timeout is short and fail fast. However, the real mitigation is bulkheading. We separate the thread pools. Service A should have a specific thread pool only for handling callbacks from Service B. Even if the main pool is exhausted, the callback pool remains free to unblock the deadlock.
Follow-up 2. Can this happen at the database level?
Answer: yes. Transaction A updates table X, then tries to update table Y. Transaction B updates table Y, then tries to update table X. If they run at the same time, they deadlock. The fix is to ensure all applications access tables in the same order, always times then Y, or use deadlock detection settings in the DB engine.
Follow-up 3. Curveball. Why is a circular dependency considered an architectural anti-pattern, even if you fix the deadlock?
Answer: it makes the services tightly coupled. You cannot deploy or scale A without considering B. It creates a distributed monolith. If B goes down, A goes down. The goal of microservices is independent deployability and failure isolation, which circular dependencies destroy.
The architect you become.
You have just survived 30 of the most brutal production scenarios in the AWS Java ecosystem. You are no longer just writing code. You are engineering resilience.
The journey recap.
1. We secured the JVM memory against leaks. 2. We navigated the black holes of the distributed network. 3. We optimized the database against throttling and contention. 4. We illuminated the darkness with proper observability. 5. We mastered the AWS SDK to prevent resource exhaustion.
Final words.
The difference between a senior engineer and a staff architect is not knowing the syntax of a loop. It is knowing what happens when that loop runs 10 million times in a constrained container at 3 a.m. Armed with these 30 scenarios, you are now ready for that interview. If you found value in these war stories, subscribe. I break down real-world system design every week. Good luck and happy debugging.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your Java job interviews like Java Application Support Engineer jobs, AWS Java Developer jobs, Java Backend Developer jobs, Site Reliability Engineer SRE jobs, Java DevOps Engineer jobs, Java Kubernetes Developer jobs, Java Blockchain Developer jobs, Application Security Engineer jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links. For more exciting tips, tricks and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.